We now know that hey, condition number is the way to figure out whether a particular system of equations is well conditioned or ill conditioned. But how do we relate this to the number of significant digits that are correct in my solution vector? So for example, we have looked at this particular theorem that delta x divided by norm of x is less than equal to condition number of A times norm of delta c divided by norm of c for Ax equal to c. So if we have a system of equations like Ax equal to c and we're making a change of delta c to the right hand side vector, it's going to make a change of delta x to the solution vector. And we have proven the theorem here that the relative change in the solution vector can get amplified by as much as the condition number when we look at the relative change in the right hand side vector. So based on this, we need to figure out, hey, how many significant digits can I trust in my solution? So we can very well say that, hey, the possible relative error which you're going to get in the solution vector will be based on the value of the condition number multiplied by what is the possible change which is going to take place in my right hand side vector. Since we are representing numbers in a floating point format, we can at least say that, hey, there's a possibility that the amount of relative error which I'm going to get just by representing numbers will be of the size of epsilon mac. So it looks like that condition number of A times machine epsilon. So we are saying that, hey, if I'm representing numbers, there is going to be some change in the number which I'm representing and the number it gets represented by that will at least have a relative error of machine epsilon. So this number here is condition number A. This number here will at least be around the machine epsilon number. So we are saying that, hey, this is equal to norm of delta x divided by norm of x. So what that means is that this gives us a sense of what the relative error in the solution vector is, and that's the number which we want to now compare with our with the number of 0.5 times 10 to the power 2 minus m. So what we want to be able to see is that, hey, is the condition number of A times the machine epsilon, is it less than or equal to 0.5 times 10 to the power 2 minus m, 10 to the power minus m. And why is it what does m stand for? M stands for what is the largest value of m can I get such that this inequality is valid. And whatever that value of m turns out to be, that is the number of significant digits which you can trust in your solution. So this goes back to the same formula which we have had for relative pre-specified tolerance of 0.5 times 10 to the power 2 minus m. The reason why the 2 is missing is because we are not talking about percentages here. This is just a fractional number right here, condition number A times machine epsilon. And so go and find out the largest integer which you're going to get for m, positive integer of m, for which this number here, the condition number times the machine epsilon, is less than this number. That gives you the number of significant. So m is the least number of significant digits we can trust. And that's the end of this segment.